putting on this computer. All right, good deal. Morning. Okay, glad to have you guys here. Very happy. Okay. So like I said, homeworks, we need to get them submitted on time. Okay. And I just talked about the formality of homework. Engineering paper is preferred, not mandatory. Okay. You can just use A4 printing paper, fine with me. Okay. If you have a blank sheet, anything, as long as letter size, that's okay with me. Okay. One thing I noticed, like I just mentioned, if you just print it out, the problem, and start writing doodle on it, sorry, I cannot read. Okay. My eyesight is pretty lousy. Okay. I've been having these glasses since I was like 10. I blame that on video games, but now I blame more on your research and the homeworks. But anyway, so if I cannot read, I cannot give you a fair grade. All right. That's about that. So try to organize it. You may say, okay, what kind of organization you're looking for? You see my notes, right? You see my horrible write-ups, right? But at least there's some logical sequence behind it, right? As long as you can follow that format, that's fine with me. Okay. All right. So there's a trick. Now, it's already too late to submit on time, but if you feel like your write-up is a little bit messed up, you worry about your grade, you can resubmit. Okay, I can see it from the system. So if you resubmit, I can still count it as on-time submission. I will not count it as late submission. Okay, if you feel uncomfortable with your write-up. Okay, all right. So I'm gonna say this only once. Okay, so pay attention. Take a look at your homework submitted. I haven't finished all the grading yet. All right, so feel uncomfortable, whatever you submitted, please resubmit. Okay, any question about homeworks? Anything else? Are we good? Okay, good. So let's continue. So what we have learned so far? What we have learned? Well, my name is Bob. We're learning reinforced concrete design. There are two components in reinforced concrete. One is concrete, the other is what? Steel, right? And what is concrete good for? Compression, right? What is steel good for? Tension. Great, you didn't eat breakfast, right? So not a lot of energy here, right? I didn't eat neither, a lot of coffee, right? So let's try it again. What is concrete good for? What is steel good for? Perfect. So you need two to work together, combine them to get a perfect from each word, right? So what we have learned again, we start learning the bending of the concrete, right? So how beam bends. I have a rectangular beam, how beam bends. One theory, plane section remains what? Plane. Plane section remains plane. What does it mean? Every section in the beam will remain straight, isn't it? So I want to have this image in your head. Stop looking at the board. Nothing's on the board right now, okay? Have this image in your head. So slices, right? Loaf of bread, slices of bread, right? We're trying to bend it. Every slide will rotate, will pivot, okay? When they pivot, you introduce tensile and compressive strain, right? So think of this way. When you bend the beam, right? Is the top part compressive or bottom part compressive? Top part, and then the bottom part is in tension, right? So what concrete is good for? Compression. So in the tension part, concrete dies. No more concrete in the tension part, right? What's remain in the tension part? Steel. And what do we assume? The working condition of steel. Steel does what when failure? Steel yields, right? Steel yields, right? What does yielding mean? Now, what is the yield strain for a grade 60 rebar? 0, well, that is stress, 60 KSI, perfect. What is strain? S-T-R-A-I-N, strain, yield strain. That is stress divided by Young's modulus of steel, isn't it? Fy over ES, right? What is ES anyway? 29,000 KSI, right? That's the modulus. So Fy, in this case, 60 KSI divided by 29,000 KSI, what you get? 0.00 207. It's a very odd number, but you will remember it. You say, how? I don't know. I'm bad. I don't even remember the password to my video game login. Well, you will remember 0.00207 because every week, at least twice, you'll be reminded. Okay, 0.00207. That is a strain for yielding for the steel. All right. What happens when steel yielded? What happened when steel yielded? Well, Bob, I don't know, becomes noodle-ish, right? It doesn't have a whole lot of strength, but it stays at the yield strength, which is 60 KSI. Why do we need to know that? Because if I have two number 9 rebar in a section, how much of an area reinforcement we have? Two number 9 bars in a section, how much area of reinforcement? 2 inch squared, right? And now at failure, the bar yielded. What is the total tension force by those two number 9 bars? 60 KSI grade 60, right? Multiply by how much? 2-inch square. What is the total tensile force? 120 kids. Great. You guys attend high school, right? You know our arithmetic, right? Basic algebra, right? 120 kips, right? So that is the total tension force. So we start from tension. In the section mechanics materials, compression has to what? Equal to tension, right? So that means I have to set equal part of compression, which is 120 kips in compression, right? How do we calculate the compression force in concrete? Well, it's a long process, but it's a nonlinear curve, right? But what we do, we don't do that. It's too much. What do we do? We use Whitney stress block. What is Whitney stress block? Think about it in your head. What is Whitney stress block? Well, I don't know. Whitney stress block. What is a block? Well, I don't know. My head, has this straight lines, right? It's a rectangular, isn't it? It's a rectangular, isn't it? So the rectangular has a width of 0.85, what? 0.85, what? F prime C, is that right? That's right. And then has a length of what? Has a length of A. What is A? Effective compressive zone. That is equal to what? Beta 1 C. What is beta 1? Some coefficient related to F prime C. What is C? The actual compressive zone size, right? And then that is 0.85 F prime C A. What else? What else? The section has a what? Width. What is the width? B, right? So the compression force is 0.85 F prime C A B. Okay, F prime C A B. Everything has to happen in your head, okay? I want you to see that. So that is compression 0.85 F prime C A B. That equal to what? Tension force. What we just said about tension force. 120 kips, right? Say if I have F prime C 4 KSI, can you not give me the effective compressive zone size A? You can calculate that. So now you have a section, right? Come on, remember, right? Recall, right? Have you watched the detective series, right? Try to put things together. We have a tension force at the bottom, 120 kips. After calculation, I know I have, say, A, about 5-inch of compressive zone side effective, right? And then I can use the distance between the compression force and tension force to calculate the moment. Is that right? So how do I get the distance? I need a lever arm, which is JD. And what is this lever arm? That is equal to the depth of the section. What is the definition of the depth? That is the distance between the top fiber to the tension force, right? Centroid of the reinforcement, isn't it? What do we call depth in terms of symbol? D, ds, right? ds or dt? ds or dt? ds, right? Now, what is dt? dt is the bottom, lowest level of layers, right? That is called dt. They're different. So what do we need dt for? By the way, we're using it to check the what? The strain in the bars. Why do we need to check the strain in the bars? Because we made assumption that steel yields. We need to know whether the strain yielded or not, isn't it? So that is the whole game. So now coming back to this point, what is the distance between the compression and tension? What is distance between the compression and tension? D minus something, right? Depth minus something. Minus what? Half A, or A over 2. Got it? Right? See, it's not hard. It's not hard, right? Now you have the distance. You want to find the moment. And what kind of moment you're looking at? M, N, right? N representing nominal strength. That is equal to what? T or C, tension or compression, multiplied by that distance. What is that distance again? D minus A over 2. There you go. Now you have Mn, right? Is it done? Are we done? No, not yet. What we're missing? Strength reduction factor. What is the letter symbol for that? Phi. Is that right? And phi for different strain in dt, right? Epsilon t, you have a different numbers, right? Say if epsilon t bigger than 0.005. What is this 0.005? What we call it? Tension controlled, right? Tension control limit. So when epsilon t is greater than 0.005, what is phi? 0.9. But what if my epsilon t is smaller than 0.002? What is phi? 0.65. Is that right? Then we're okay because now we know phi. Say it is 0.9. Then what is design strength? Phi mn, 90% of mn. Then we're done. Okay, that's how we learn. 2 weeks. This is pretty much we learn. How much time we used? 5 minutes, 6 minutes? Not much. Okay, so some of you complain. Reinforced concrete is a long memory business. You got to remember all the procedures, equations, right? So how do we do that? How did I do it? Every morning I recite it. Every morning I recite it, right? Then you remember it. Okay, so before you start doing your homework, don't jump in. Think about it in your head. Has to have some logic sequence, right? So the way I go is tension first, and let it equal to balance the compression. Find out the compressive size, find the distance, and get your moment. Okay, so that's my sequence. You don't have to use this sequence, whatever works for you, but you got to have your system. Okay, all right, so that's a good review. We're done with review. Now, let's look at some fancy business, right? Let's look at some fancy stuff. So here, lecture 4. Well, I should still continue of lecture 3, okay? Lecture 3. We're talking about design of, not design, actually, analysis of singly reinforced, okay? Single layer, well, did I say single? Actually, multiple layer, right? We went over that last time at the end of it. Multiple layered section, okay? That's where we're at. Oh, yeah, sorry. How do I do that? It's all off now. This is my favorite part, battling with technology every day. Sorry, Alicia. Let me see if I can do this again. Yeah, all right, let me restart. Okay. Okay. 1 second. Okay, now. Oh, it's even worse now. Let me see if I can do this. See anything? Yeah, wonderful. Pale and greenish, whatever the color is. Okay, that is, how about this one? Yeah, I tried all buttons and it's apparently. You see, you can see anything? And they had some issues last week. I think Magdi also have a problem with this. Abdurham, that is professor. Yeah. It's horrible. You don't see any physical button on the side. I just go around trying to play with it for a second. How you know? It comes in handy one thing. I always worry about wasting money on my clothes and everything. Benefits of that after all. Okay. All right. So let's talk about it. We have an example last time, right? What do we do last time? We have a section. Well, you know what? Sorry, but I can use our last time's notes and finish this part and start with a new one. Okay. So last time we have a section like this. 4 number 9 bars at the bottom. we calculate the center of the 4 number 9 bars and find out the depth of it is 16.5 inch. Okay. Now, quick thing here. I have 4 number 9 bars. They are spaced 2 inches apart. Okay, spaced 2 inches apart. And let's just say if I'm trying to find the distance between the center of these two rows, right? It's got to be 1 inch here, and this is be 3.5 inch. And 20 minus 3.5 inch is 16.5 inch. That is faster than find out centroid of the group of bars, isn't it? That is faster, right? Can you always do that? Can you always do that? Answer is no. Why? Because I got lucky. I got 4 same bar size. If the bar are different size, you cannot do that. So the safest bet is always go with equation. Okay, don't just pick the center of the group of bars geometrically. Okay, geometrically. All right, got it. Okay, quick thing. So now we got a depth equal to 16.5 inch, and we did the whole thing, right? Find out the compressors on side C, check the strain, and we left at a happy smiley face. That is the strain in the steel is, well, not so happy, slightly lower than the tension control limit. What does that mean when you see this? Well, first, it's bad, right? It's now 0.05. So I know that phi is not 0.9. It's probably smaller than 0.9, isn't it? Somewhere between 0.65 and 0.9. But is this one bigger than 0.00 or not? Yes, right? What does it mean? It means what? Steel yielded. What's so good about yielding, Bob? When yielded, I can always say that the stress in the steel equal to what? Grade 60 equal to what? Equal to what? 60 KSI. There you go. So that's where I'm getting at. Trying to make sure I know the stress in the steel. And when the strain yielded, I know that it is 60 KSI. Why do I need to know that? Because ASFY gave me the total tension force where I start with. This is where I start with 4 inch of 60 KSI. Remember? You say, Bob, you know that. Why are you doing this again? I'm confirming that. Don't forget, this is assumption at that stage. This was an assumption at that stage, right? At first, nothing happened, right? It's not like the Bible when God says something. It's just we make things up. We make it up. We don't know. All right, we don't know. And now we confirm that this is 120. Sorry, 4 minus 6 KSI. That is 240 kips. All right. Okay. So that is why we're doing this. We're confirming it. Okay. Now we know tension is this one, and this business is about under reinforced, over reinforced. I have recorded this and it's uploaded to YouTube. In case you forgot about it, you can go back and take a look from last class's office hour. But now let's continue this. I know the tension force is 240 kips. Okay. I want to find out my nominal moment capacity, which is Mn equal to T and lever arm. What is the lever arm here? We just said tension force multiplied by distance. What is distance here? Give you a hint. ds minus what? A over 2. Great. Okay, you got it, right? So now Mn equal to a 240 kips, and get your calculator ready, right? I didn't do this myself over the week. I'm lazy. Remember, Bob is a lazy guy, right? I need your help to calculate the number for me, right? 240 kips minus A, what is A? 5.88 inch divided by 2. Okay, so can somebody give me a number of this? Can you do it? Pull out your calculator. Let's do it. Come on, a lot of fun, right? ds is 16.5 inch. Okay, that is the depth of it. Okay, 240 kips multiply 16.5 minus 5.88 divided by 2. Come on, I need a number. Anyone? Should I start giving points? 3,000. Louder, please. 3,254 kips, right? And inch. Great. Okay. So are we happy with this? I will deduct 2 points from this nice lady because we need to convert to foot, right? And then help me out, please. To convert by foot, divided by 12 inch per foot, and what you get? 271.2, something like that. Okay, so just say Kip's foot. Do I get a second? Are we okay with this number? Good, okay. You got to second me. If I'm not, we're just gonna keep going. I did that before, okay? So I'm not embarrassed if something like that's your fault, not mine, okay? All right, so that is my MN. Okay, now phi, strength reduction factor. You remember the equation for strength reduction factor? Do you remember? Do you? Because I sure don't. I forgot about it. Okay, I'm dumb. I don't know. Right? I just lazy. So what I do? I draw my drawings. Okay. So what the phi looks like? This is phi. Horizontal axis. What I use? Epsilon S or epsilon T? T. There you go. Epsilon T. Not epsilon S. Okay. Not epsilon S. You say why last time? Well, we happened in one row. Yes. This one not to one row anymore. So this case, when I have epsilon T smaller than 0.002, what is my phi? 0.65. If it's bigger than 0.005, what is my phi? 0.9. There you go. So I draw a line like this and draw a line like that, and then in between, linear interpolation. And where you add it, actually, this slope here is 250 divided by 3. Okay. Now you have this information. Do you now remember the equation? Duh, I remember it. Why? Because now phi equal to 0.65. It's the beginning of the step, right? I start climbing the ladders, which is whatever epsilon T minus 0.002 multiplied by the slope, which is 250 divided by 3. And that, ladies and gentlemen, is my equation for phi. See how I remember it? You can do the same to simplify, okay? Dry equation will never stick your head. You gotta have some graphic, have some image to go with it, okay? Make life easier. All right, so now what is my strength in epsilon T? No, let's copy it down. Phi equal to 0.65 plus what is epsilon T here? 0.0046 minus a 0.002 and multiply 250 divided by 3. What do I get? Folks, come on, your turn now. Don't disappoint me, please. Let me hear some number. Use your calculator. 0.65 plus this fellow minus 0.02 and multiply 250 over 3. What you get? 0.87 exactly. Do I get a second? All right, good deal. So now what is my design moment? Phi Mn equal to 0.87 multiply 271 Kip foot. And what do you have, guys? What do you have? Don't stare at it. If you forgot your calculator, bring it next time, okay? Bring it next time. You will need it for this course. What do you get? Any number? 235. Do I get a second? Yeah. All righty. We're moving on. Wonderful. That's it. Is it hard? Is it hard? If this happened in exam, can you not ace it? Of course we will, right? It's simple, isn't it? All right, this is simple. What if? Let's make it more interesting. Okay, just like in the casino, right? You pass the first tiger machine. Now we're doing Russian roulette, right? Let's play a little more, right? Red and black, what's the number, right? Let's play a little more, right? Same section, nothing has changed, but I'm going to change my reinforcement. How am I going to change my reinforcement? Give me 1 second. Let me see if I have the old lecture note 3. Okay, I don't. I'm really going with fly today because I didn't put the notes on it. Okay, so you guys really have to help me out here. Okay, I don't know the number that is. I don't know. I have no idea. Okay, so now bear with me with 1 second. Let me at least have some backup plan here in case I mess up again. I always do something crazy, right? 291.4 spring. I think I got this one. Okay. Okay, so this is my old notes. Okay, but let me share my thing here. You can see this still. Okay, where is my share screen button? Let me do share screen again, share screen. Okay. No, you guys don't see it? This thing, I'm telling you, slow and groundhogs anyway. Okay. let me just remove this thing somewhere here. Elisa, sorry, okay, I gotta move things around a little bit. Okay, so not too bad. All right, let's open now. Say, now I have my section, okay? Same thing, nothing changed. The section remains the same, right? What is 20 inches, good. So 12 inch of B, height is 20 inch. I'm not changing a thing and everything stay the same in the sense of that still number 9 rebars at the bottom, okay? And this distance here, what do I have here? Well, since it's 2.5 inch. Okay, but instead of 2 number 9 rebars in the bottom, I have 4 number 9 rebars here. Let's make it a little bit more beefy, right? 4 number 9 bars. And the top row is the same, right? I'm going to put 2 number 9 bars. I have a choice now, folks. I have a choice now. If it were up to you, will you do configuration number 1 or configuration number 2? Which way you will do? Will you do? I got 3 number 2, 1 number 1, number 1, 2 number 1. One time. Even now 3 to 3. Which way, which way, which way? 2, 4 over 3. Which way, which way? Is like audition, right? Auction, right? Which way, which way? Number 2 or number 1? Number 2, okay, 5. Okay, 6, 7 seems more. Number 1, okay. 8, 8 over 4. Anybody else? Anybody want to bid? $1, $2, $3? Which way? Which way? You want to put it on the side or you want to put it in the middle? Imagine you're in the field, right? Frozen out there, right? Freezing, it's cold, right? And you want to put the bar there, fix it. How are you going to fix it? You use what? Stirrups, right? What a stirrup looks like. Something like this. Isn't it? So who said number 1? Somebody, right? How are you going to tie that? Where are you going to tie it? You have to chop. You can, right? You can still, you have to chop a bar, right? Cut a small piece, right? And you go this way, isn't it? You were in the Scott, right? You know how to tie nuts, right? You tie it like here. You tie it like here. Then you put number 1 here. That's a whole lot of work, isn't it? Instead, right? We mark in the stirrups and just tie here, and that's it. So in this case, number 2 prevail, right? When you don't have any support, you do on the side. So preferably, when you go to the field, you put the 2 extra bars on the side, not in the middle. Okay, small details. All right, you know it. Okay, now we get it. All right, good deal. So we have this again. Spacing between the top and bottom rows 2 inch. Okay, I want to do a lot of work today. Okay, so bear with me. I want to find the centroid of this whole thing. So how to find centroid? Use the equation, right? What is the equation? What is the equation? Sigma A area per each row and yi distance of each row divided by the total area of AI, isn't it? That's very abstract, right? Let's speak English, right? So that is in the first row. If I say the bottom of the first row, how many bars? 4 multiply 1 inch square, so 4 number 9 bars, and multiply distance 2.5 inch. Where that 2.5 inch coming from? I'm counting from the bar to the bottom reference line here, okay? Bottom reference line here. So that is distance plus a 2 multiply 1 inch squared, multiply 2.5 plus 2, so 4.5 inch. Divided by total area, 6 inch square. I have total 6 number 9 bars. Right? Can I get a number on this, folks? Pretty easy, right? Can I get a number? Do I have to do calculation in my brain, in my head? Come on, some number had to come out of it. What is it? This is 10, just so you know, and this is 9, just so you know, this is 6. Come on, before I finish, you better finish it, right? What do you have? Come on, what do you have? Somebody? 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 You're slower than me? Oh my God. What happened? Calculator doesn't work? Come on, do it. Check my number at least. Confirm, is it okay? Is it right? Okay, good deal, thanks. So that is the distance. Okay, so where we at? We're here. We're at 3.167. So let's just say 3.17 inch, so round it to 2 digits. Okay. rule of thumb for reinforced concrete. If you go with strain, 0.00207. That is three effective number. Stress, kips, and everything, 2 digits after that. Okay, just our rule here. Okay, make things easier. Okay, I don't want to see crazy running up issues. Okay, so that is the center of it. Now, what is the depth? ds equal to what? H minus y bar. So H is 20 inch minus 3.17. I cannot do that. That's too much. What is it? Come on. What is ds? Help me out. Come on. 16.83. You got it. Confirm. I confirm that, right? That is the depth of it. Now you have depth. Let's do. What's the first step now? What is the first step? Step number 1. This is all so far prep, right? I'm preparing myself. Okay. What is first step? Where we start? Tension, right? What is tension? T equal to what? What is tension? T equal to AS, what? Grade 60 FY. What is it? 6 inch squared multiplied by 60 KSI, 360 kips. Good. And then with tension, I'm talking about compression. So tension equal to compression, A equal to AS FY divided by 0.85 F prime C. Okay. And then A out and B, and this is 360 kips. Again, folks, help me out here. Divided by 0.85, and let's just say 4 KSI of curbside concrete, and width is 12 inch. And what do I get? Come on, move your fingers, please. What do you get? What is my A? What is it? The hard? 8.82. Immediately, you know, this is what? Much larger than the last example, which is 5.88, right? Much larger, right? Now, let me ask you this. If you're a seasoned civil engineer, like I like to claim myself to be, I have a larger compressive zone. I feel nervous. Why I feel nervous? Now, the concrete compressive strain at failure is what? Epsilon Cu is what? 0.003. That stays, right? Larger the compressive zone is, lower tensile strain my reinforcement is. So immediately, I think I may have an issue of whether that steel will yield it or not. I start to get worried. Okay, my compressive zone is too big. Why you say it's too big? What is the section height? H equal to what? 20 inch. So if my section height, right, compressive zone is close to 50% of the section height, I have a problem. The golden numbers is 40%, close to 40%. Okay, if it's 40%, yeah, I'm okay, right? 60%, 50%, no, I have some problem. Okay, I'm gonna show you. So how? Let's pretend nothing happened. Sky is blue, grass is green, right? I can still play video game and my wife will never find out, right? I can do that. 8.82 inch divided by beta 1, 0.85, folks. 4 KSI concrete. What'd you get? Come on. 8.82 divided by 0.85. What'd you get? Let's do it quick. 10.4 inch. Do I get a second? Okay, good deal. So that is my effective compressor, sorry, actual compression C here. Okay. Now, without doing anything, let me just go ahead, start doing the diagram. Remember the 20% free credits, right? So strain diagram looks like, so strain looks like this. Epsilon Cu equal to 0.003. And I have some strain in the bottom here, epsilon S. And I want to do my stress, but before I move on to stress, right? This is strain, this is stress. And suppose I will do internal forces and everything, right? Before I move on to that, let me see this. I have a depth of ds equal to a, what is my ds? 16.83 inch. Okay, and I have my concrete compressive zone C equal to 10.4 inch. Okay, and I can calculate the strain in my rebar now. And this is not a bottom, this is just the group of the bars, okay? The center of the bar. So before I do the 20% free credits, okay, I want to do that. So use the similar triangle, epsilon Cu divided by C should equal to epsilon S divided by ds minus C. So epsilon S should equal to ds minus C divided by C multiply epsilon Cu, right? So DS is 16.83 inch. C is 10.4 inch divided by 10.4. Come on, use your calculator. Epsilon CU 0.003. You just said it. What is my epsilon S? Strain in the rebar. Come on, do it. Help me out. Anything? Anything? You know the number already? Be careful. I'm going to call you next time, okay? Now, what is it? What is strain in the rebar? What is it? Come on, do it. I really don't know my stuff, okay? We're risking it together, okay? Every day the problem changes. I don't know, right? It's like in a casino again, okay? What is it?
0.0018.
Okay. Do I get a second? Okay, good. Are we happy? No, we are very, very scared. Okay, we are very, very scared. Why? Why? Smaller than 0.00 what? 207. Okay. What we do? What we do? Well, I don't know. I'm a tough net, right? Let's just continue, right? I mean, it's bad. Let's see how bad. Because I'm given the section. It's not like I'm going back to design it anyway, right? I want to proceed. Shall we? Sure, you can. Nobody said you cannot, right? So how to proceed at this level? What is the consequence of this? All promises has been broken. Nothing happened anymore. What is the first priority or first promise assumption we made? Steel yielded. It does not yield, right? So what we do iterations. Now, with this, I say, okay, I need to calculate the stress in the steel now. So Fs, which is stress in the steel, equal to modulus of elasticity for steel, ES, multiplied by epsilon S. What is ES? 29, 29, come on, 1,000, KSI, folks, remember that. And multiply 0.0019. And what you have? Come on, do it. What you have? Give me a number. Louder, please. 55.1. Do I get a second? All right, good deal. So that is much lower than the yield strength. And to make a correction, this is not KIPS, this is KSI, okay? Stress. All right, so now that is taken care of. So the total tension force become what? AS, still area multiplied by FS, but instead of yielding, I have 55.1 KSI multiplied by 6 inch square. And what do I have? Come on, do I need to finish myself? 3. Exactly, great. That is total tension force. That means I'm going back to step 1. What is step 1? Trying to find what? A. Remember, effective compressive side. We're going back because tension force just changed. And now that is AS, FS 0.85 F prime C B. So 330.6 kips divided by a 0.85 and multiply 4 KSI multiply 12 inch. What you have? Come on, let's do what you have. 8.10. Do I get a second? Do I get a second?
Yeah.
Okay, good deal. So that is the new effective zone. Okay, effective compressive zone. So if that's true, what is my actual compressive zone? C equal to A divided by beta 1. That is 8.1 inch divided by 0.85. What do you have? Come on. What do you have? 9.53. You're gonna ace the exam, lady. How about the rest of the class? Do I get a confirmation? You also want to get 100, right? Good, good, good deal. Okay, so that is the actual compressive zone size. What to do? What to do? What do you do? I don't know. It's like, I don't know, cyberpunk, right? It's like endless cycles. You play that video game, the most lousy game, all kind of bugs, never get out of it, restart, you know, worst review ever. You don't play. I feel sorry for you, but I played, right? It's a horrible game, right? What happens? You have to restart the whole game now because what happened? Actual compressor zone changes. So epsilon s changes as well. So ds, remember, minus c over c multiplied by epsilon cu. And that is 16 point, the depth not changing. What is depth? 16.83 minus 9.53 divided by 9.53 and multiply 0.003. What you get? Epsilon s equal to what? Come on, help me out. Deja vu, right? Help me out. Different number, same process. Help me out. What you have? 0.0023. Okay. Confirm?
Yep.
Yes. Is that better? Sure, that is better. So what happened? What just happened? We went through one iteration. We changed the strain in the steel from unyielded to a yielding point. Is that right? Okay, so now tension equal to, so let me finish this, right? So that is larger than yield strain of 0.00207, right? And then it go back to what? Go back to the tension force. So T equal to AS Fy, because this means stress in the steel equal to yield strength again. And that went back to 6 inch squared. Multiply Fy is 60 KSI. This is 360 kips. Okay. Have you seen this number before? Have you seen this number? Yes. Where did we see it? At the beginning of the problem. Long time ago. Remember, before everything happened, before Luke's your father, you know, everything, right? Before everything happens. So that means we'll go back to square one, and that's where we started with. Okay, that's where we started with. What does this mean? What does it mean? It means that we're on the borderline. Is that right? We're on the borderline. So which way do we proceed? We will proceed with this number right here. After 2 or 3 iterations, we will proceed with this number here. Okay, that's what we do here. So we will proceed with this number. So that means the strain will stay under the yield strain, because use this number, what strain you get? Remember, we did that already. Epsilon s equal to what? 0.0019. Okay, so at this point, we will use this strain to judge the strength reduction factor phi, but we will still use Mn equal to T and distance D minus half A, where T is this 360 kips. Strange, right? Strange, right? But that's how we do it. Why? 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 Because we keep the yield strength of the bars, okay, to increase the nominal moment resistance. But considering we are risking here, so we're using a lower strength reduction factor to be safe. So this is the compromise. Okay, this is the compromise. All right. Okay, so let's finish it. So if this is the strategy, right? So I'm gonna go find the Mn. That is ASFY 360 kips and multiply distance ds. What is ds, folks? What is ds? 16.84 inch. Is that A4? Is that right? A3? A3, sorry. See, I told you I made a mistake. And A, what is A? What is A? Which A do we use? Which way do we use? We use the original A. Which is the original A? 10.4. No, 10.8. That is C, right? Sorry, you're right. What is A here? 8.82. You're absolutely right. 8.82. Okay. And divided by 2. So Mn equal to this number right here. Do I get a number out of it? Come on, help me out. Help me out. Help me out. What is it? $372.6 kip foot. Good. Do I get a second? Good. That is my nominal capacity. Now phi. I need to use my stress reduction factor. What is the equation for phi? 0.65 plus epsilon t minus 0.002 multiply 250 over 3. What is epsilon t here? I don't know. I don't know. I really don't know. Why? Because I used epsilon s. Remember 0.0019. Remember that was just the judging whether it yielded or not. Okay, has nothing to do with epsilon t. So how do I use epsilon? How do I find epsilon t? I use the diagram. Then this is epsilon cu 0.003, and this is c, which is now 10.4. Is it 10.4? 8.82 divided by 0.85. I think it is 10.4. Yeah, 10.4. And this is ds. But I'm trying to use dt. So dt is what? What is dt? dt is equal to h minus the concrete cover, 17.5 exactly. Okay, so now let me just put this on the side to calculate, right? Epsilon t should equal to what? Should equal to what? dt minus c divided by c multiply epsilon cu. So what is dt? 17.5 minus 10.4 minus divided by 10.4 and then multiply by epsilon cu. Come on, what you have? What you have? Let's do it. .002. Do I get a second? Spot on. Okay, good deal. Now with that, what is my fee? 0.65 plus what? Say again?
We don't have to do that.
Yes, yes, you're right. So plus 0. 0.65, right? That's it. Because it's not yielding, right? Now let's take a look. So that is 0.65, right? You don't have to do anything. So now what is mm? 0.65 multiply what? 72.6 cubic foot. What do you get, folks? What do you have? Come on, come on. 0.65. Come on. 2 what? 242.2 cubic foot. Do I get a second? Anybody? Agree, disagree? Come on, I need a confirmation. Important to me. Good. So this is second case. What do we learn? I don't know, Bob. You draw something, I saw it, and that's what we learned. Well, yeah, I did that, but we did 2 examples today, isn't it? Well, finished the last example, but did one more example today, right? First example, 20 inch of section height, 12 inch of width. How many bars we put in? First example, 4, number 9 bars. Is that right? And what is that capacity? What is it? 235. In the second example, how many bars we put in? 6. And comparing to 4, what is the percentage increase? 50%, isn't it? I would say that's quite a lot. Would you agree? Increase 50%, that's a lot, right? What do you expect? I expect I get 50% the moment resistance, right? Because that's my thought, right? Because steel is expensive. Steel is expensive, right? What'd you get? What you get? 242. How much of an increase? Almost nothing. So answer me this. Can you blindly add steel to your section to make it stronger? No. Remember this, okay? On the job site, if somebody said, oh, not enough capacity, put steel in it. You say, go back, take Bob's class. Got it? Okay, all right. See you on Wednesday, and I'll show you a different way of changing it, and much better. Okay, thank you so much. Alisa, thank you for being online. Okay, I'm just gonna close out, and I'll upload the notes, and you'll see it. Okay.
Thank you.
Yeah.
Is that on YouTube somewhere?
Yeah, I think last time's lecture, I think I recorded it, but the problem is the last time we didn't have this screen. But the notes is uploaded, so you can take a look at the notes first. Yeah, you're in the track team or anything? Football. Okay. Yeah, good. May teach me something next time. All right, see you later, man.